Welcome to the Differentiation series. Differentiation has a wide range of application, including mathematics, theoretical physics, applied physics, engineering, and many more. Differentiation is a method of finding the derivative of a function, which can be carried out by algebra manipulations using basic derivatives, rules of operation, and the knowledge of how to manipulate functions. Overall, differentiation is a gateway to nearly all fields of higher mathematics. Welcome to the first session of the differentiation series. In this video, we will briefly introduce the concept of differentiation and learn to do differentiation using the first principle. We will learn how to evaluate limits according to the properties of limits. In addition, we will introduce various rules for differentiation, particularly the power rule and the chain rule, illustrated through 10 worked examples.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything.
Welcome to the series of differentiation, and this is the first session of this series. Let's start with a gradient of a curve from the point P to the point Q as shown in the diagram. As we know, the gradient of the line PQ is calculated by the rise over run. If m sub pq is denoted as the gradient, it equals the y-coordinate at q minus the y-coordinate at p, or over the x-coordinate at q minus the x-coordinate at p. Now, in order to derive the expression of the gradient at the point P, we assume the x-coordinate at P is a, and the corresponding y-coordinate is f of a. In this case, the point Q is moving towards the point P. Then we assume the x-coordinate of the point Q is x, so the corresponding y-coordinate is f of x. So the gradient at point P, which denotes m sub p, which equals f of x plus a minus f of a, all over the result of x minus a as x approaches a. This leads to the general expression of the differentiation by first principle. The derivative function f prime of x equals dy by dx, which can be written to the limit of delta y by delta x as delta x approaches 0, which equals the limit of f of x plus delta x minus fx all over delta x as delta x approaches 0. Please note the notation of the derivative function f prime of x can also be expressed as dy by dx, y prime d f of x by dx, d sub x of y in various occasions and circumstances. Now let's talk about the properties of limits. The assumption here is that the limit of f of x equals p as x approaches a, and the limit of g of x equals k as x approaches a. The first property is that the limit of any constant as x approaches a certain value a is the same constant. The next property is the limit of a constant k multiplies fx as x approaches a equals the constant multiplies the limit of f of x as x approaches a. The next property is the sum or difference property. It states that the limit of f of x plus or minus g of x, or in parentheses as x approaches a, equals the limit of f of x as x approaches a plus or minus the limit of g of x as x approaches a, which equals p plus or minus q. The following property is the product property, in which the limit of f of x multiplies g of x as x approaches a equals the limit of f of x as x approaches a multiplies the limit of g of x as x approaches a, which equals p multiplies by q. The last one is the quotient property, which states that the limit of f of x divided by g of x, or in parentheses as x approaches a, equals the limit of f of x as x approaches a over the limit of g of x as x approaches a, which equals p over q. Now we start to show how to apply the properties of the limit along with some algebra techniques through a few worked examples. The first example is to find the limit of the square root x minus 3, or over the result of 9 minus x as x approaches 9. The initial observation tells us that both of the numerator and the denominator equals to 0 when substituting 9 into the expression. Hence, we need to do something with the expression so that we can substitute 9 into the expression. As we can see that the denominator 9 minus x can be factorized to 3 plus square root x, or in parentheses times 3 minus square root x, or in parentheses. As for the numerator, since square root x minus 3 can be written to negative open brackets 3 minus square root x close bracket. After cancelling the term 3 minus square root x, the expression becomes the limit of negative 1 over the sum of 3 and square root x as x approaches 9. It equals negative 1 over 6 after substituting x by 9. Here example 2 is to evaluate the limit of x minus 2, or over the result of square root of 5x minus 6 subtracted by 2 as x approaches 2. Since both numerator and denominator of the expression would become 0 if x were substituted by 2, we then multiply both numerator and denominator by the conjugate of the denominator, the sum of square root of 5x minus 6 and 2. Hence, after simplifying the expression, it becomes the limit of the sum of square root 5x minus 6 and 2, all over 5 as x approaches 2, which equals 4 over 5 after substituting x by 2. Example 3 is to evaluate the limit of the square root of x plus 1 subtracted by 1, all over x as x approaches 0. Since we can not directly substitute x by 0 to the expression, however, we can do a bit of algebra transformation by multiplying both numerator and denominator by the sum of square root of x plus 1 and 1, or in parentheses. Hence, the limit expression becomes 1 over the sum of square root of x plus 1 and 1 as x approaches 0, which is 1 over 2 after substituting x by 0. Example 4 is to evaluate 4 limit expressions. As for the first question, x cubed minus 8 is factored to x minus 2, or in parentheses times a quadratic factor, which is x squared plus 2x plus 4. After the factor x minus 2 being cancelled, the expression equals the limit of x squared plus 2x plus 4 as x approaches 2. So it equals 12 after substituting x by 2. Here we apply the same technique for question 2. After multiplying both numerator and denominator by the conjugate of the numerator, the expression becomes the limit of h on the product of h and the sum of square root of x plus h and square root of x. After being simplified and h is substituted by 0, the limit equals the reciprocal of 2 square root of x. Here we continue to work on question 3 of example 4. Since we cannot directly substitute x by 0 in the expression, we multiply both numerator and denominator by the conjugate of the denominator. After being simplified, the limit equals the limit of the modulus of x times the sum of the square root of a plus x and the square root of a minus x, all over 2x as x approaches 0. Up to this point, since the numerator has a modulus of x, we need to look at the situation of which direction x approaches 0. When x approaches 0 from the right, the limit equals x times the sum of the square root a plus x and the square root of a minus x, all over 2x, which equals square root a after being simplified. When x approaches 0 from the left, the expression equals negative x times the sum of the square root a plus x and the square root of a minus x, all over x, which equals negative square root a after being simplified. In summary, the limit expression equals square root a as x approaches 0 from the right. It equals negative square root a as x approaches 0 from the left. In question 4, the limit is multiplied and divided by its conjugate. Thus, it becomes the limit of 3x plus 2 all over the sum of square root of 4 times x squared plus 3x plus 2 and 2x. After both numerator and denominator being divided by x, and then substituting 1 over x by 0, the limit equals 3 over 4. Example 5 is based on the function f of x equals a times x cubed plus b all over x, given that f of 1 equals 4 and f prime of negative 1/3 equals negative 1. The question is to find the values of a and b. Since f of x can be written to a x squared plus b over x, its derivative f prime of x equals 2ax minus b over x squared. After substituting x by 1 and negative 1/3 to the function fx and its derivative function respectively, we have two simultaneous equations, a plus b equals 4 and 2a plus 27b equals 3. After solving the simultaneous equations, we obtain the value of a, which equals 21 over 5, and b equals negative 1 over 5. The function given in example 4 is y equals x to the power of negative 1/3, and the question is to find an approximate value for 1 over 0.9 to the power of 1/3. Based on the first principle, we can calculate the approximate value of the reciprocal of 0.9 to the power of 1/3. Hence, f of x plus h approximately equals f of x plus h times f prime of x. Based on the given function of fx, we can find its derivative f prime of x, which equals negative 1/3 times x to the power of negative 4 over 3. Hence, f of 0.9 approximately equals f of 1 plus f prime of 1 times negative 0.1. After substituting the values of f of 1, f prime of 1, the reciprocal of 0.9 to the power of 1/3 approximately equals 1 over 1 to the power of 1/3 plus negative 1/3 times negative 0.1, which equals 31 over 30. Now let's briefly introduce a few important rules in differentiation. The first one is the linear rule. As it can be seen, the derivative of a constant function is 0. That is, if a is a real number, then dA by dx equals 0. If f is a differentiable function and a is a real number, then af is also differentiable, and daf of x by dx equals af prime of x. The next is the sum or difference of two differentiable functions u and v are themselves differentiable. Moreover, the derivative of u plus v or u minus v is the sum or difference of the derivatives of u and v. Generally, the derivative of au plus or minus bv equals au prime plus or minus bv prime. Another rule we are going to explain here is the differentiation of ax to the power of n by applying the linear rule as well as the first principle rule. The derivative of ax to the n equals a times the limit of x plus h, or in parentheses to the n minus x to the n all over h as h approaches 0. After expanding x plus h, or in parentheses to the power of n, using the binomial expansion formula, the term x to the n shown in red is cancelled. Then, after being simplified and substituted 0 to h, its derivative is an times x to the power of n minus 1. Now we're going to introduce one of the most powerful differentiation rules, the chain rule. This rule deals with composite functions. If y equals f of u is a differentiable function of u, and u equals g of x is a differentiable function of x, then y equals f of g of x is a differentiable function of x, and then we have dy by dx equals dy by du times du by dx. The proof uses the technique of multiplying and dividing by the same non-zero quantity. Here we assume that g of x does not equal to g of c for values of x other than c. So the term g of x minus g of c is multiplied and divided by the first principal expression. Hence, the derivative dy by dx equals the limit of f of g of x minus f of g of c all over g of x minus g of c as x approaches c times the limit of g of x minus g of c all over x minus c as x approaches c. Hence, we have proved the chain rule. Example 7 is to find the derivative of composite function sine f of x. We now apply the chain rule to this example. Since the derivative of sine function is its corresponding cosine function, after the chain rule being applied, its corresponding derivative function is shown on the screen. Example 8 is to find the derivative function of y equals square root of 3 times x to the 4th minus 2 times x cubed plus 5x plus 1. We may start to introduce a variable u, which equals 3 times x to the 4th minus 2 times x cubed plus 5x plus 1. Then we apply the chain rule to this function. So dy by dx equals dy by du times du by dx, which equals d square root u over dx times d3 times x to the 4th minus 2 times x cubed plus 5x plus 1 on dx. After being simplified, its derivative function becomes 12 times x cubed minus 6x squared plus 5 all over 2 times square root of 3 times x to the fourth minus 2 times x cubed plus 5x plus 1. Example 9 is to find the derivative function of f of x, which equals x squared minus 8, or in parentheses cubed. We start by assuming a function g of x equals x squared minus 8. According to the chain rule, f prime of x equals df by dg times dg by dx. Hence, f prime of x equals 3 times x squared minus 8, or in parentheses squared, times 2x, which is simplified to 6x times x squared minus 8, or in parentheses squared. Example 10 is to find the derivative function of f of x, which equals 10 over 3x minus x squared, or in parentheses cubed. We still apply the chain rule to find its derivative function. Since f of x can be written to 10 times 3x minus x squared, or in parentheses negative cubed, x prime of x equals 10 times negative 3 times 3x minus x squared, or in parentheses to the negative fourth times the derivative of 3x minus x squared, or in parentheses. It finally equals 20 times 2x minus 3, or in parentheses, or over 3x minus x squared, or in parentheses to the fourth, after being simplified. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.